Today, rather than kind of delve into a lot of my research, what I'd like to do is actually give a bit of an introduction to the field that I work in, which is the field of quantum networks. So hopefully throughout this talk I can kind of explain to you a little bit what a quantum network is. I think it's actually not quite as well known as I'd like it to be. The kind of technologies that we're working on to build these kind of large-scale quantum networks, and then also give a bit of an outlook into what's happening in the field and where things are going. So I'd like to start with a very quick kind of physics background and introduction. I promise I won't get too into the weeds. But just kind of, to start out, right, in classical computing, right, like what's happening in the laptop I'm using to present here, everything is made of these bits. And so it's basically just a 0 or 1. You can really kind of think of this if you just kind of had some number line that I have something, it's in one state, it's in another state. And usually this is kind of whether or not you've like physically trapped, for example, an electron. But with quantum, we actually use something slightly different, something that we call a qubit, which is just a fancy way of saying a quantum bit. So we write them a little bit differently, but in addition to the way that we write them, you can kind of still think of quantum bits as being in a 0 state. You can think of them as being in a 1 state, but where it starts to get really interesting is you can actually live, for example, somewhere in between these. You could kind of be in this, what we call a superposition of 0 and 1. But actually the full story is that you really can't think of this just as a number line, for example. You actually kind of need an entire sphere to really think about what the actual state that you have here. So usually quantum states are characterized by these kind of two angles, theta and phi. Theta is kind of this polar angle that tells you how much of the 0 or 1 state that you have. And then there's also, very importantly, a phase relation between these two states, which we kind of call this parameter phi. And then the last thing that I'll kind of say in this introduction is that when you start dealing with multiple qubits, you can kind of have these special states. We call these entangled states, where information about one of these qubits can actually tell you information about the other qubit. For example, if I have this kind of psi-type Bell state, I either have one of my qubits in a 0 state and the other is in the 1 state, or it's the other way around. So if I measure one of the qubits, I can kind of learn something about something else. And so I think one of the questions that I get asked quite a lot when I tell people about the kind of work I do is what is a qubit then? Like, how do you actually make a qubit? Which I think is a really interesting question. There's kind of a couple different ways you can do it, but usually you just kind of want to pick some kind of energy levels in some type of system. And so one example here is kind of looking at, for example, trapped atoms or trapped ions. I think this is one of the coolest pictures ever taken. This is actually a very long exposure photo where that tiny little dot that you see in the center is actually an individual atom that has been trapped using optical tweezers, or if you're kind of using ions, you can be using electric or magnetic fields. And so these typically have some kind of energy level structure that looks something like this, where you have these different orbitals and then different Zeeman sublevels, different hyperfine sublevels. These are all just kind of further splittings of these original orbitals. And then you can see here that there's a variety of different energy scales that you can use, and you would just kind of pick two of these levels to make as your qubit. Another example is kind of these superconducting qubits. This is what a lot of companies are currently using for like quantum computers. Here I show an example of the Google Sycamore quantum processor. And if you were to zoom in very, very far into this image, you'd see a bunch of what you see here kind of at the bottom right, which are what are called Josephson junctions. So these are these kind of nonlinear elements. For anyone familiar with kind of electrical engineering, if you think of a normal like LC oscillator, you have some kind of harmonic oscillator type energy structure. And so this is kind of an anharmonic element that would break that harmonicity such that you can kind of isolate two of these levels. And this is, again, kind of usually at somewhat of the gigahertz scale. And kind of the last major category, I think, of qubits is looking at, for example, defects in solid state. This is a very, very broad category. This includes a lot of things such as quantum dots. There's also some sorts of defect complexes where you have multiple different atoms and vacancies, or you can kind of be looking at single defects. So these can exist in silicon, and diamond are very well studied. And the example that I show here is what I work with in my lab, which is a single rare earth ion sitting inside of some kind of host material. And so again, here you have these kind of orbital energy level structures. Here it's kind of these 2F energy levels. These kind of get split when you put them into a crystal field. The kind of local environment will affect some of these energy levels. And then some of the other structures that are present inside this crystal, again, kind of Zeeman sublevels, hyperfine sublevels, will also give you further splittings. And you can see again that you kind of have a wide variety of energy ranges that you can use. And so once you have qubits, a very interesting question is, well, what can you do with them? Like, what are actually useful quantum systems? And I think, again, there's kind of three major categories of things that you can do with this. One of these is communications, doing things like cryptography, authentication, kind of secure voting protocols. And I think we'll actually be getting a talk tomorrow about some of this in a bit more detail. Computing, doing things like simulation, especially kind of a lot of things that you would do with a modern supercomputer. There's a lot of things that quantum computers can do that would take a supercomputer thousands, if not millions of years to do. And one of the slightly lesser known fields, but I think actually one of the most near-term useful fields is quantum sensing, looking at magnetometry, gravimetry. There's also a lot of more recent proposals to do things like dark matter searches and a lot of other kind of astrophysics applications. But the one thing that I'd really like to emphasize in all of these different applications is that the true benefit that you get from using quantum comes not just from having individual isolated computer sensors or communication systems, but it really comes when you start to connect multiple of these systems. When you have multiple computers connected, multiple sensors connected, and not just multiple, but the fact that they're at distance from each other. And so in the field of quantum networking, this is really what we're interested in. It is how you connect remote quantum benefits such that you can truly get all of these benefits. And so there's kind of, three things if you're trying to think about building a quantum network that you might kind of ask yourself in terms of the requirements that you need. And I think that the things that you really need here are to be able to send quantum states, these kind of entangled states that I talked about on this first slide, between different locations. You'd like to be able to do this all with kind of very low noise and very high fidelity, right? You want this to be very, very efficient. And ideally, you'd be able to do this very, very quickly, right? Like modern computers kind of run on gigahertz timescales, so that's pretty much what you'd like to do. And if you want to send information over very long distances, I think that's kind of the first thing. Like I said, you want to be able to send these quantum states. You might ask yourself, how do I do that? What is the most efficient way to send information over very long distances? And it turns out this is actually a very, very well-studied field already. We've been looking at this for many, many years, and optical photons are actually the, without question, most efficient way to send information over long distances. A lot of internet is actually sent right now over optical fibers that exist all across the US, across the world. There are fibers running from here to Europe, for example. And there's kind of certain wavelengths that are actually very, very efficient that you can use to send information. And so in this kind of 1.5 to 1.8 micron range, what we call the telecom band, if you've ever heard of kind of telecom stuff in relation to classical internet, you can actually get down to the point of about 0.3 dB of loss per kilometer, which means you would be able to send an optical photon about 10 kilometers before you lose your information. And because there's already a very extensive fiber infrastructure in place, you can kind of leverage this as you were to try to build up your own quantum network. So you know that you'd like to use optical photons. Then the question becomes, how do you generate those photons? And ideally, you'd like to be able to generate single photons that you can use for all of your applications. And there's kind of two ways that you can do this depending on how you wanted to set up your network. In one of these formats, what I kind of call this emissive network, your end node, be this a sensor, a computer, whatever it is that you'd like to be connecting, can actually emit optical photons. So if you remember kind of on some of those examples of qubits that I showed, some of these have transitions in kind of the hundreds of terahertz range, which is actually the optical range. So there's a lot of platforms that can already kind of just natively emit different types of photons. And again, also, some of these defects in solid state, defects in diamond and silicon, REI here is kind of rare earth ions. All of these already kind of have that functionality a little bit built in. The other format is this kind of absorptive network, where you have some specific dedicated entangled photon source, be this some kind of quantum dot, some kind of nonlinear crystal that you're pumping with some kind of light, and then the different nodes would then absorb some photon, and then you still have some kind of detection format to be able to tell that you've actually created these entangled states. And so this is great. We can now create optical photons. But if you remember just a little bit ago, I said that you can get about 10 kilometers before you lose half your signal. But if you wanted to, for example, have a quantum computer or sensors connected between here and New York, that's about 7,000 kilometers. So there's absolutely no way that you could do that. So you also need some format to be able to send things over long distances. And in classical networks, it's very easy. You stick an amplifier in there. Unfortunately, you do not have that option when you're dealing with quantum states. There's something called the no cloning theorem that basically prevents you from doing that. So you need some kind of alternate method to extend the distance over which you can send quantum information. And to do that, we have what we call quantum repeaters. And so the quantum repeater protocol kind of says that, say I have two distant nodes that I'd like to entangle. Rather than trying to directly entangle these nodes, what I can instead do is break this up into a bunch of smaller nodes where I have these repeaters in the middle. Then I can kind of establish entanglement between these outermost nodes, and then establish entanglement between these kind of intermediate nodes and the very center node. and then do a very specific operation. We call this usually a Bell state measurement, where you can actually kind of concatenate this entanglement. And I can basically carve out these kind of two states on each side. And then I do just the very same thing in the middle here, and using this you can kind of herald entangled states over very, very long distances. And so again, kind of some of the platforms that you would use for like these quantum repeaters, a lot of the same things I've already mentioned. And so the final kind of technology that I'd like to talk about is I showed, again, a lot of different examples of things that you could use for qubits, and I showed that you have a lot of different energy scales that you can use to define your qubit. And depending on the application that you're looking at, you might want to use some of these energy scales over others. But to connect these in an optical network, again, you still kind of need to have everything in this hundreds of terahertz range. But for example, superconducting qubits, which are kind of one of the leading platforms for computing, all operate in the gigahertz range. So you need some way to bridge this very, very large, like orders of magnitude energy gap. And to do that, you use something called a transducer. And so I won't get too into the weeds here, but the basic idea is I have something, for example, a microwave photon, which is at like the gigahertz scale, and then I have some object in the middle here that can kind of mediate this interaction and convert this to an optical photon. And so this can be some kind of electro-optic material where I'm sending in, again, this kind of electric microwave photon, and then the material has this kind of native ability to convert, or I have some kind of optomechanical mode inside my crystal. Again, many of the other platforms that I talked about for quantum networks already have transitions at both of these energy scales, so you can leverage a lot of different things here. And so I'd then kind of like to give some examples of things that we've done with quantum networks. You know, once you connect all of these, there's actually a lot that we've already been able to do. So one of these that I think is really cool is we've actually, in addition to being able to use optical fibers, we've actually shown that you can use satellites to do entanglement over very, very long distances. This was a work done in China where they created an entangled state between two nodes kilometers apart, actually through a satellite. We've been able to show already that you can kind of build very small scale 3-node networks. The first ever 3-node network was actually this project co-led by a former postdoc in our group, where again you can see that they have these two nodes, Alice and Charlie, and they use Bob to do this kind of quantum repeater protocol that I just showed, where they do entangled states between Alice and Bob, between Bob and Charlie, and then they can actually concatenate those. There's already been examples of what I like to call blind quantum computing, where you can have some kind of client connecting to a very, very strong quantum computer. In this case, you could kind of think of this as analogous to a supercomputer. But here, the client is able to do computations that the server does not know about. You can completely eliminate all of the information that they have access to. Distributed quantum computing, where you take some kind of computational task and you split it up over two different computers that are completely separated. And this is actually really, really important because in a lot of quantum computing, one of the bottlenecks that we're running into is it's really hard to make a lot of qubits on a single chip. So if you can make two different chips and then split your computational task up, it allows you to do a lot more. And one of the last things I will talk about, if you're kind of just looking at pure like entanglement generation, you can do what's called multiplexed entanglement, where you're able to do a lot of things in parallel and generate these entangled states at a much faster rate. So trying to move towards these kind of gigahertz speeds that I mentioned. And one of the first examples of this ever done in solid state was actually published just a couple weeks ago by our lab here at Caltech. And so kind of looking forward, I'd just like to end with a little bit of, I think, where the field is at and where I think a lot of things are going. One of the really, really exciting things is that we're actually starting to build these kind of test beds and move out of the lab and into the real world to test these things out. So I show here on the left, this is an example of a quantum network that was built in the Netherlands between Delft University and The Hague. On the right, this is an example of one that's being built in Boston, connecting Harvard, MIT, and the MIT Lincoln Lab. There's also networks in Chicago, in DC, in China, and a bunch of different areas. And so we're able to kind of really start testing these in real-world settings, but there's still, I think, a couple challenges that need to be addressed, namely the scalability of these things. You know, to implement a really large-scale network, you need thousands and thousands of devices. So a lot of the fabrication, we need to figure out how to be able to do a lot of this stuff more efficiently. And unfortunately, all these technologies really, really do suffer from their efficiency and the rates you can do things at. I showed you an example of a 3-node network, and that's about the biggest that we've done so far. So to kind of get to the point that we envision of having really thousands of devices connected, there's still quite a lot of work to do. And so with that, I'd like to acknowledge, while I didn't necessarily talk about too much of what we did, our group at Caltech, the Ferron group, where we try to build a lot of these different types of technologies. As I mentioned, we kind of specifically work with one class of materials, which is rare earth ions in solid state, but working towards building these end nodes, these repeater nodes, and these transducers using these. And with that, I'd like to thank you all for your attention, and I'm happy to take any questions.